All right, so today we're going to be doing lesson 4, voltage breakers and conductors. Um, and for the people on YouTube, if you haven't seen the previous lessons 1 to 3, then you might want to go back and look because we're going to be referencing them, referencing lesson 1 or 2 here and there. Let's go ahead and get into it. So the types of voltages, there's several different types, but the type that you and I are going to come across most often are in the delta and the Y configurations. And they're named so because this is how the transformers are wired up. I mean, it looks like the delta symbol, and this is obviously looks like a Y. So the delta, the voltages, whenever you're looking at voltages on the delta side, these are going to be your primary voltages, 120, 240 single phase or 240/120 three phase. Now, whenever it's single phase, it's normally just a single transformer. You don't have the other two, and it's one transformer. And this is what most residential houses have, just single transformer up on the pole, and that's it. The other location where I see 240 delta three phase is industrial facilities. A lot of them don't need neutrals, so why would you install it? 240 is a lot more efficient than 208 when it comes to amperage and conductor loss and everything else because it's just a bunch of motors. So places like the oil and gas, industrial parks, a lot of them have just 240 setups. When it comes to why the 120 208 single phase is pretty rare. I've seen it a couple of times. It's normally just a single transformer. It can sometimes be two, depending on how much they're needing. Same thing with the 277 480 single phase, single transformer, sometimes two. I wouldn't rely on the one or two transformers up on the pole just because there's a lot of other configurations out there that I'm not even touching because I only see those every once in a while, and I'm just trying to cover the most common things here. So if you look up at the pole and you're like, hey, I see two transformers, well, there may be something else going on, but just do your homework or call me or somebody else. Now, the nomenclature that I have shown here is based mostly on the ANSI C84.1 standard. And what that is this table comes out of that standard. What you can see here is where I got that nomenclature at. Yes, they're not using the delta because I don't know, whenever they typed this up, they didn't have the delta symbol or whatnot. I add it just because it's a lot more simple. And you can obviously see 3-wire single phase. So this is going to be single phase voltage here and here, whereas this is 4-wire, which means it's 3-phase. And yes, there's a lot more medium voltage, high voltage stuff. Like by definition, these are all medium voltage, high voltage, so on and so forth. So the public will see like danger, high voltage signs all over a lot of electrical equipment, but it's not by definition high voltage, just saying, hey, be careful. 98% of the public doesn't have the knowledge that, hey, there's all sorts of these voltages. If you ever get a chance to go read this standard, I highly recommend it just because this is the standard that says, hey, utilities, you have to maintain certain voltage parameters to be in compliance. You can be plus or minus 3% of whatever you're supposed to be pushing. You can have so much drift between the voltages, so on and so forth, unbalance, stuff like that. If you ever get bored and having insomnia, that's a good one to read. So, all right. One thing you can always rely on, though, is looking at poles with 3 transformers. Okay. You can actually look up there and tell how these are wired. So whenever you've got the corners connected together like this, what you see here, and then all the corners are connected, that's going to be a delta. Like, period. That's a delta. You can't get 208 or 480 out of that. By the same token, if you see all the middle tabs connected, that's going to be either 208 or 480Y. Now, I was actually able to find a picture I took up in Pittsburgh to show what this looks like. And whoever installed this, like, they're never this clean. Whoever did this did a great job. I was very impressed. That's actually why I took a picture of it.
But you can actually see what's going on.
Yeah, exactly. I was like, oh man, that's awesome. I'm pretty impressed. So, but you can clearly see, the middle tab on these things are connected all the way around, and then they're pulling off, creating the Y with the other ones right here. So, so the color coordination is the other thing I wanted to point out is the NEC defines a color coordination, but it also caveats to, hey, look, if your local jurisdiction has something else, follow that. The only change from that, this shall be this color, is on a delta. When you have a highlight delta, the B phase has to be orange. Like, period. There's no way around that. Okay. So whenever you have a highlight delta, you're going to have a neutral here. But if you just have a straight up delta configuration, there's not going to be a fourth wire. Okay. It's just going to be 3 wires with no neutral. And what that looks like this, and the reason a highlight is so dangerous is because, whenever you install, say, receptacles, for instance, a receptacle is supposed to have 120 volts. Well, on A to neutral and C to neutral, you do have 120 volts. But when you put a breaker on B phase, you've actually got 208 volts, and that'll destroy pretty much anything that you put in there, like a lamp or something that's going to tear it up. So that's why you've got to be very careful with that. And I'll show you what a panel looks like here in just a second. Where it's
it mainly, I'm assuming it's mainly orange because that's the one where voltages get weird when you connect that with something else.
That is correct.
Like it's like the identifier, like, hey, if this is delta, if this is the delta high leg, this wire, like, be wary, because if you connect it and other things, you're going to get different things. But for sure the other 2 wires and neutral will get you 120. And is that kind of how it works, why they do it that way?
That is exactly why they do that like that. It is you have to pay attention to this, heads up, watch out. Now, the fun part about this is up until 1984, I think, somewhere around there, either late 70s, early 80s, somewhere around there. The convention, the unspoken rule was the high leg goes on the C phase. So I've come across it where it is an actual high leg delta and the orange is on C phase. And when we did work out there, we had to annotate, hey, the high leg C phase, be wary, be careful, don't connect anything like that. And we had to reflect that in the panel schedule as well. So, but most of what you may be working on, it should technically be on B phase. Don't move it. If you find it on C, just leave it as is and annotate it. But nowadays, it is a requirement for it to be on B. Now, the acronyms that I use, the color coding for the acronyms is, it's black and red for 120, like that. That's standard. That's in every single household. This is what that looks like. You got red, neutral, black. Okay, so phase, and neutral, obviously. And it doesn't matter, which one, red's on the left or red's on the right. That doesn't matter. The 240 delta's going to have the orange in the middle, which I don't have a picture of here. But the color coding for the 208 or the 480, I always remember it. Be right back, boy. That's just how I remember it. I don't know where that came from. I picked that up one day, probably from somebody else. But that's how I always remember it, because it's black, red, blue, or black, orange, yellow. And you can see that, reflected in so you got black, red, and blue. And then you've got brown, orange, and yellow. And obviously, white, gray, always going to be neutral, period, like across. That's a given. Same thing with the ground, green or bare copper. That's always going to be a given across the board.
The code recognizes this ANSI standard of the coloring of wires.
The ANSI standard is how it is written.
Oh gosh, the ANSI standard is how it's written. The coloring, like, is that where does that standard, or where does that come from?
So the coloring suggestion comes from the NEC, with the exception of the high leg orange, white and gray being neutral, green, bare being ground.
Gotcha.
That's an NEC standard. You shall have this color.
Gotcha.
Now, local jurisdictions can actually overwrite the phase conductors, especially on a 208 or 480 system. So places like Duke, CPS, AEP, like they are allowed to have different color codes. And And if you're ever doing a design, you actually have to make sure that their color codes match up with NEC, which most of the time they do. Sometimes individual cities will have different color codes, and you can see all sorts of random stuff out there for that, especially in Florida. I've kind of noticed that Florida has, you look at some of their requirements, and it's like, you want what now? Just
like you don't have to be special.
exactly, but that's what they
Gotcha.
want. So
So
and
it's a go to the local, like doing a project is go to the local and see how they are doing it, and then double check with the like actual standard. But at the end of the day, the local standard can override the like NEC standard.
yes,
Okay.
that is correct. So, and as a minor side note, you can see that it is completely legal, 100%, to have black conductors all the way through and mark them, phase mark them with colored electrical tape, colored E-tape. That is totally fine. This is 100% acceptable. Like, it is blatantly out. It is well stated. You can do this. However, what I have actually done on multiple occasions, and I found it online on Google Earth, you can actually purchase color-coded installation for no additional cost.
Wow.
And it's kind of hard to see here, but
I see the red, white. I see it could be red or orange and blue, maybe black.
Yep.
Definitely see
So
like a white.
yeah, so this is red, white, and blue, and then black.
So for the 480.
480, yes, exactly. I drove by this one day and I was like, oh, that's cool. It's
Pretty
red, white, and
cool.
blue and black. Yeah. Like, I'm glad I'm not the only one that calls out for colored insulation. So, but that's, places like Southwire, it costs nothing to have colored insulation. And when you're putting in hundreds of thousands of feet in a campus or, a treatment plant or whatever, it's just go with the colored insulation. It's so much easier for future, people troubleshooting that.
Can the person inspecting like say, hey, you need more, even if yes, this is acceptable, can they come out and say, hey, like I want you to provide more color coding or whatever? Can they do that?
The short answer is yes. Like if somebody only took one round turn on this and it was not blatantly obvious that this is meant to be the red conductor, the AHJ can say, hey, look, you need to identify this better. And what that means is come and put several round turns on this thing so it's clear that this is, a phase conductor. This is the red phase conductor. And every now and then they'll do that just because, sometimes the stuff gets dried and starts falling off. And then by the time, 10 years goes by, this may fall off completely. And then you've got two blacks and you don't know which one's which.
Gotcha.
So yes, that's about as far as I can go, though. Let's just say, hey, identify this better. So the breakers, I've included 3 pictures of common configurations. Well, I'll show you a different style breaker here in a minute. But I did want to show, hey, look, this is a single phase or a single pole, and that's annotated right here. When you see this is going to be either 120 volts or 277 to ground.
Because it's single phase.
Exactly. Yes, on 240 or 208, it's going to be 120 volts to ground. On a 480 system, 277 to ground. And that's, it's just a single phase to ground. This is what we'll just say the receptacle is seeing, or the exhaust fan or whatever. It's just seeing a single phase. Now, here's the confusing part. When you get 2 poles, it is still technically single phase. So that's why you have to, that's why you have to specify, hey, look, I've got a 240 single phase fan, or I've got a 480 single phase HVAC unit, something to that effect. When you're in the 208, 240, 480 voltage, but you still only got 2 poles, that's still single phase. There is no 2 phase, as it were, or two.
Yeah.
There's no 2 phase. It's either single phase or 3 phase, and that.
And if you're not using every single pole, it is single phase, even if you're using the higher voltage.
Yes, exactly.
Doesn't mean the panel's not a like a three-phase panel, but the connection is single phase to the three-phase. Is that correct? Because like you can't, like that 480, that is a three-phase panel. You're just connecting two poles to it, making whatever equipment you're connecting to single phase, just using two poles. Is that correct?
Yes, that is an accurate understanding. And then again, it's, of course, three phase. So yeah, it seems like you got your head wrapped around that one. So here are a couple of panel boards that I've come across. You can always quickly identify something that may be 240 high leg when you have random breakers being skipped, especially when you have two singles and a skip. So the reason they didn't put breakers here is because you'd be reading 208 to ground. So like you couldn't put a receptacle on this one, or on this one, or on that one, or on that one. Like all of these would be blank if these were all single poles. And it's not as clear here, but they just kind of randomly skipped side by side. Most people are like, "Oh, why didn't they just push this 2-pole up?" Well, they could have. Technically, they could have. Electrically, it would have worked totally fine. But they were trying to help show, hey, look, this is a 208 high leg. And you can actually see, somebody put a piece of orange tape right there indicating that's the high leg phase. So a lot of electricians will actually do the installs like this to help other people identify, hey, look, this is not a 240 panel. This is not a 208 panel. This is 240 high leg. Does that make sense?
Yeah.
Okay, so in short, if you get random stuff being skipped, recognize this may be a 240 high leg.
Can you at all in any way, shape, or form connect anything to those?
Oh yeah.
Like
yeah.
You can, as long as it's the right, it's just as long as it's the right voltage, yes, you can.
Unless you know the math, you should not. However,
Gotcha.
on a 240 high leg, I have been known to actually put a 208 single phase hot water heater neutral to ground.
Gotcha.
It's 120, 240 panel board, and I had 208 because it's a high leg, and that's the only hot water heater we could get. Well, great. I mean, technically it works, but there's more math that has to be done outside of the normal panel schedule. Like, it's just there's more stuff you have to contend with. So technically, yes, but unless you know exactly what you're doing and know and understand the math, don't do that.
Is there applications where you have to use the high leg, or is there always a better option and sometimes you end up using it? Like, does that make sense? Because of this, you're kind of wasting space on this panel by having to skip certain things. Like, is there something better you could choose to avoid this wasted space, I guess, is the question I'm asking.
That's a great question, actually. 90, 95% of the time, utilities will not install a high leg anymore, period. Like, they don't. This is, from way back when, 50, 60, 70 years ago. These are all legacy installs. However, there's been 2 instances where I actually was able to get the utility on a new service to install a 240 high leg. I had, we'll just call it like 380 something amps worth of 3-phase load. Like, it was a massive industrial facility, nothing but motors, like across the board. That's what it was motors. And I just needed a couple of receptacles. And it didn't make sense to install 208Y because that would add more load, cost the client more money for the install. Like, it just overall would cost more. If I just need a couple of receptacles, like we're talking 10, 15 maybe, pull that neutral on a 240 Delta and be done with it. It's much easier, cheaper, because you got to remember, as voltage goes up, current goes down. So if I have less current flowing through there, my conductors don't have to be as big.
So there is very specific applications where the high leg does make sense to use, but it is definitely not a typical like go to use every time kind of thing. Like if you can avoid it, but use it if it actually makes sense.
Correct. Yeah. And like I said, there's only been 2 instances that I can remember off the top of my head where it's like, this is exactly where a 240 high leg would come in handy.
But nowadays, like you said, like the ones that are still this delta, whenever you get to it, it's like, geez, now we have to think about this. Like instead of, wow, it could have just been this and this would have been better. But it's just how it was originally installed, and you have to work with it because that's what they have, unless they're demoing and doing whatever with it.
Exactly. Yeah. I mean, once you have your head wrapped around the math that goes behind, the B phase calculations, it's not that bad. It's not that scary. It's just a lot of engineers don't come across it, so they don't understand. Hey, this is a little bit different. It's to me, it's no different than doing like an open delta or something. So, an open delta is when you don't have the third transformer, but you still have 3 phase. It's called a ghost leg. Yeah, and most of the time you can actually see where you've got a larger transformer and a smaller transformer, and 4 wires coming off of the pole. Well, that's an open delta that has very specific applications too. But there's like 6 or 7 different configurations out there. I'm just showing you 2 because those are going to be the most common.
Gotcha.
Yeah, those are really good questions.
What you're saying is though, if I ever come across like a weird one that's not the typical, which you normally see typical, if you come across something that's different, that's when you get someone involved and be like, hey,
yes, exactly.
Have you seen this? What do I do?
Yep. Yeah. And what's funny is I've talked to quite a few of the engineers here, and most of them are like, yeah, no, I don't know how this last idea. Like the other double E that you worked with there frequently, and that I work with, he calls me up about once a month saying, hey, I come across something else. I need your input. Like, yep, okay. And it's by sheer happenstance that I get into all this. A lot of it was all small town installs that are all 100 and something years old, and that was sheer happenstance that I kind of fell into the knowledge of all of this. So breakers. All right. So breakers can look like this, where you have what looks like 3 individuals that have been super glued together. You can also have breakers that look like this, which this technically isn't legal, but this is. So these are 2 single pole breakers that have been connected by this little bar right here. Like this is a totally a legal install, as long as they have a quote unquote permanently affixed device to turn off both at the same time. Then this is a legal install, because this is a single pole breaker. This is a single pole breaker, but it's feeding a single phase 2 pole load.
Gotcha.
Copper here is not quite legal. It does the job, like it makes it obvious.
It doesn't look safe.
Yeah, it's not.
Let's put a metal bar on electrical equipment.
Yep.
And be something you're touching.
Exactly. So, and I mean, this is the same thing. Like this is totally legal. There's nothing wrong with this one. And I'm pretty sure this is a 3 pole breaker. They look like they're super glued together. Well, pretty sure this is a 3 pole breaker. Other ones you might come across look like this, where it's only got one handle and this other side's blank. Well, this is still a 2 pole breaker. It's just a different style.
Because at the end of the day, it's look at it as how much space it's taking up. Like
exactly.
A single is taking up 1 little slot. If it's taking up 2 slots, whether it's 1 little handle or not, it's still 2. It's taking up 2 slots, meaning it's 2 poles, and then so forth. If it's taking up 3, it's 3 poles.
Exactly, just like that. That is taking up 3 slots. I did want to point that out because some people get tripped up on that, but it's very clear to see 3 slots, 2 slots. So 3 pole, 2 pole. So we're going to move on to types of conductors. Okay, so the most common in our industry are copper and aluminum. I found this from somewhere, I don't remember exactly where, but I thought it did a really good price comparison on cost. So for instance, if I need 65 amps worth of ampacity, this is going to be, it's going to be basically 76 cents a foot, because that's price per 1,000 feet.
Mm-hmm.
However, if I go with aluminum, it's going to be roughly 25 cents a foot. So it's a third of the cost to go with aluminum. So that's one of the many reasons a lot of installers are actually putting in aluminum in like residential places.
Mm-hmm.
It's roughly a third of the cost. I mean, you're not running anything large. It's all number 10, number 12, number 8, like smaller stuff. So spend a third of the less money, pass it on to the client, be done with it. There are some disadvantages about going with aluminum. I'm not going to get into that here. If and when you come across that, let me know, and I'll walk you through the things that you got to put in the drawings and what you have to pay attention to if you're working on aluminum. But we'll cross that bridge when we get there.
Apart from a client having potentially in their specs or standards or whatever that you have to use copper and they don't accept aluminum for their projects or whatever, is there anything else that would make you have to use copper over aluminum, like that you don't have a choice?
The NEC actually, the NEC does not allow for aluminum in certain hospital situations. Like it requires copper in certain installs inside hospitals, and that's for the reasons that. Well, I'll go ahead and get into it actually. So when you let me pull it back there. All right. So this is actually a panel board I was working on the other day. These are aluminum conductors. All right. The entire house was installed on aluminum conductors except for the ground. Grounds, yeah. Not gonna get into that. If you look real close, you can see this big, huge goop of stuff. This is called Noalax. It's a name brand, but all it is essentially an antioxidant, so that the aluminum doesn't start oxidizing, not allowing ampacity to flow through it. So you know how metal rusts?
Mm-hmm.
Well, aluminum doesn't rust. It actually oxidizes. It forms a very thin, we'll call it rust, or a thin layer of rust on the surface, and that inhibits more of it from rusting. That's why aluminum, quote unquote, doesn't rust. Well,
It protects itself pretty much.
Exactly. Well, you don't want that to happen when you're trying to pass amps through here, because it doesn't go through the oxidized layer very well. That's why you dope it up with a bunch of Noalax.
What happens if you don't do that? Apart from, like, is it if you don't have that on there and like it oxidizes, like, do you just not get power going? Like, can anything bad happen?
It can actually. It's a great question. What happens is this terminal right here, where it physically connects to the conductor, like metal to metal, will actually start heating up because you have I squared R losses. Well, you have the same amount of current, but you got R increased.
Like it can't go. It's not going. Oh, like you're creating resistance, is what you're pretty much saying. Like, so
exactly.
It gets hot and and the energy needs to go somewhere, so it rejects in heat. Like heat comes off to reject the energy being like stopped, I guess. Is that what happens?
For your understanding, if that's what you need in your brain, yes. You've kind of got the cart before the horse, but it's totally fine. It heats up.
Gotcha.
You have increased resistance between the conductor and the terminal. You get I squared R loss, so you get lower voltage on the conductor, which then increases the current because more power is required. It's essentially a runaway, just long term. Months, years. This will start heating up and start melting.
Gotcha.
The other thing you've got to be concerned about with aluminum, and this is why they don't use it in hospitals very often, specifically can't use it, is because aluminum expands and contracts at a larger rate than copper does. So as you heat up aluminum, it's going to expand more than copper. Now, yes, most, if not all, terminals on breakers and equipment are rated for aluminum and copper. If you're using aluminum, you have to verify it, but regardless, most of them should be rated for aluminum and copper. Well, every 5 years or so, you come back and re-torque these terminals. Make sure they're still torqued down, because over time that expansion contraction will sit there and work that terminal loose, that terminal screw. So you can actually have a loose connection, which also increases heat. Yeah, those are two of the main concerns you got to have with aluminum. So yeah, copper and aluminum. And all right, so let's look at conductor sizing. There's a very great long story over the asininity of the American wire gauge, AWG. That's what you'll hear it called. That's what you see right here. It's, if you ever get bored, go read it, but just understand there's a crossover here at like number 1. The larger in size you get, the smaller you physically get. And then the larger in size here you get, the larger you physically get. And I was able to get a decent, picture of common wire sizes. I wanted to get several KC mil in here, but I couldn't find it. All right, and what I mean by KC mil is all of these numbers are based on the thousandths of a circular mil. So KC mil, that's how they're sized. So for instance, let's go on to number 12. It is 6.5 KC mil. And instead of saying, hey, I need a 6.5 KC mil conductor, I just need a number 12 conductor. So all the way up to 4/0. So this is, a number 12, a number 10. We don't really use number 11. Number 12, number 10, 8, 6. Let's see what they have up here. Yeah, 8, 6, 4, 3, 2, 1. Those are the most common that we use. And then these are pronounced 1/0, 2/0, 3/0, and 4/0. Okay. They can be written either way. Most of the time I see them 4/0, but just don't say 4/0 or 4/0. It's 4/0. Following with that KC mil concept, when you get into the actual KC mils, like 250, that's 250 KC mil, 300 KC mil, so on and so forth. Like the KC mil continues increasing, and that's when you get from number 1, 4/0, 350 KC mil. Like that's how you say that. Yes, it is slightly confusing. Like I said, there's a whole lot of stuff behind that, the reasoning, whatnot. That's just the high level basics. Okay, yeah, we'll get into that here in a second. All right, so there are essentially 4 different types of conductors as far as the physical configuration. You got solid, which we call out most of the time number 10, number 12, like especially residential, all of that's going to be solid. And it is literally a solid chunk of copper. Then you have concentric, which is the second most common. It's just a bunch of strands strung together, stuck in insulation. Now, if you need smaller physical size, but still the same ampacity, you can get either compressed or compact. Most of the time I see compact on like medium voltage stuff, and compressed is more on the low voltage stuff, like 600 volts and below. But
Gotcha.
if you hear that, just think smaller physical wire, but still the same ampacity as whatever the number is. It has not reduced ampacity. It's just taking up all the extra little space in here. Hopefully that makes sense. And you may never come across that.
Is it's still doing it any kind of way? Is it still the same amount of material?
Yes.
Okay, same amount of material, just is one like more efficient, effective than the other? Or it doesn't really matter apart from space if you have an issue?
Essentially, the only physical difference, the only difference between them is physical size of the conductor itself. Because like this one is going to be able to have the insulation within the upper and lower lines, whereas this one, the insulation should be outside of the upper and lower lines.
Gotcha.
So it's going to be physically larger. The only other thing I can think of off the top of my head is, when you have concentric, it's going to be a little bit more flexible, whereas the compact is not. Like these individual copper strands are going to have a harder time sliding against each other because there's no air between them. But
Gotcha.
that's on the install side, so as long as you're not doing something stupid on the installation, like, oh, let's put this on a very tight bend radius. Well, if you're not doing that, don't worry about it. The reason for all that, it's a great segue. I'm going to reference lesson 2, lesson 1. All right, so if you remember, amps is 1 coulomb per second. And a coulomb is 6.24 times 10 to the 18th electrons. So if I have a conductor and I take 1 point in it, let's just do this so it looks like an actual conductor. So over the course of 1 second, if I have 6.24 times 10 to whatever going that way across this point in this conductor, that is 1 amp.
Okay.
All right. So that, yeah, the quantity of copper here is the same as here. And what that matters is as I have amps coming through this conductor, they're going to be bouncing all over the place. Yes, generally going in that direction, but they're still hitting each other. They're still hitting the outside, hitting the inside. Like there's friction in there, if you want to call it that.
Mm-hmm.
That friction is going to cause heat, just like if you rub your hands together. If one of these electrons hit each other, or even get close to each other, they're going to start creating heat. Well, copper melts. Like it has a specific melting point. And if I know if I have 200 amps going down a conductor, it's going to provide so much friction, so much heat going down there because of the I squared R loss. Okay.
Mm-hmm.
If I increase the area in which those amps can flow, come on, that's going to not allow them to hit as often to each other or the outsides or however you want to look at that. So as I increase the conductor size, I'm not going to melt. I'm less likely to melt it, and I can push more amps down it. That's why the larger the conductor, the more amps you can push down it. I can shove more. Oh, we were talking about water. That's what it was. It's kind of similar to water pipes, right?
Mm-hmm.
I can run a certain psi and I can run a certain GPM, but if I surpass either one of those, then I'm going to rupture my pipes.
Yes,
Same thing
correct.
here.
Yeah.
Yeah.
Same thing, just with electricity.
With electrons, yeah. So I should say lesson 1. Oops. So that's why we have to have larger, because the electrons are literally flowing through this thing, hitting each other, hitting the sides, whatever else. It's going to cause heat, and that's why you go up to allow more to pass through. Yeah, that's enough of the physics on that one. So this is out of the NEC, right? So we've got copper conductors over here, aluminum conductors over here, 60, 75C, 90C. All right, so the reason these columns are different is because conductors are rated at different temperatures based on what they melt at. So if they start melting at 75C, well, you can't push 90C worth of amps through them. Like it's not going to work because they will start melting. By the same token, if you have 90C conductor, but you have 75C terminations, the terminations will actually start melting. And I've seen that firsthand. One way we get around that is, for the record, all terminations in any single panel board are going to be rated at 75C. That is an IEEE requirement. Could they handle 90C? Yeah, probably. But IEEE says these are going to be rated at 75C, period, even if they can go up to 90C. I think that's a safety thing. I'm not quite sure why they did that, but just understand if you're connecting to a panel board, your conductors have to be rated in the 75C column, even if they're 90C conductors, because you're limited by the weakest link or the lowest melting point in this chain. Does that make sense?
Yeah.
Cool. One way we can actually get around that is 75C conductors to 90C. And then between these two 90C conductors, you can actually decrease the conductor size because it's rated for more amps. These terminations
Gotcha.
aren't going to melt at anything lower than 90C. Like I've actually done this when you get, 100, 200 foot runs of something. It just makes better sense to hit 90C conductors, run at 100 foot, hit 90C conductors again, and then go into whatever the load is. Or even if your load is rated for 90C, like, great, you don't even have to hit the second set of terminations. The next thing I want to talk about was in the NEC 110.14 Charlie 1 Alpha. It high level, it talks about not if your stuff is rated at 100 amps or less, you have to assume 60C terminals. Okay. If you have not read this, or anybody on YouTube, if you're not familiar with this, go read it. I'm just giving it a high level, not really doing it justice, but go read it. And in my Uglies book and in my NEC copy, I have basically marked out this section of the code to help me remember when I'm in anything less than 100 amps, I have to be rating off of the 60C column. Just understand, like, if you're anything number 2 or below, pull it off the 60C column. And if anybody gives you grief, go give them this. And if they still give you grief, there's a link right here, which I will also put in the YouTube description, just so that you've got it, that talks about why and how and the NEC requirements for that. So, do you have an Uglies book? I don't remember.
I do.
Okay. If you want my recommendation, take a pencil and mark out the 75 and 90C column. Mine is page 73.
70 ampacities of insulated conductors, page 73 for me.
And while she's doing that, anybody on YouTube, if you don't know what an Uglies book is, there's several different ones. The one that I use all the time is this one. But obviously there's lots of other ones. I've got 4 or 5 of these things just picked up through the years. These are incredibly handy. Not the full NEC, but they have excerpts from the NEC for exactly what we're talking about. The ampacity conductor table is in here, and I've got all my stuff tabbed, and I use this multiple times every single day when I'm designing. So I marked it out with a pencil. That way I can still see it if I need to. And also put the reference at the very top of the page in red ink. That way if anybody asks, I can point them right to it. And that hadn't changed in several years, so I don't think it will.
But there is in the link that you show below is the reasoning as to why they do that.
Yes.
Why do they give it if you cannot use it?
Because there are still instances where, like, if you know for sure that your terminals that you're landing on are rated for 75C, great, you can totally use it. And that's why I said, hey, I recommend putting it in pencil so that you can still read it.
Gotcha. But if you do not know, you should assume that they are not rated for that and they're rated for 60C.
Yes, because there's exceptions in there saying, hey, if this, then 75C is fine. But unless you can verify this, or this, you have to use 60C. The last thing I wanted to talk about is the different tables for this stuff. So this is table 316. And this is specifically for not more than 3 current carrying conductors in a raceway, cable, or direct buried. So essentially that's, if you got 3 normally current carrying conductors, which, phase A, B, and C, the neutral doesn't count, ground doesn't count, and you're in a raceway, which is essentially a conduit, you're in a cable, or you're directly buried in the ground. This is your ampacity. The reason for that is that that raceway, the earth, that's basically an insulator. So as you have heating on that conductor, it's going to hold in and retain that heat. However, if you turn the page in your Uglies to page 74, there's a whole new table. Ampacities of insulated conductors, single insulated conductors in free air. And in that table, if you notice, for instance, number 12 in the 60C column is rated for 30 amps, whereas in here it's only rated for 20. Well, the reason you can get 10 more amps down that conductor in free air is because you don't have the insulation. That heat can rise and get out of there, and that's not going to melt the conductor.
Oh,
So
that
there's
makes
several,
sense.
yeah, there's a couple of different, free air. There's the one that I've got up. There's 2 or 3 others in there. I'm quickly looking through my uglies, but I don't see them in there. But the NEC has a couple of them. There's also several derating factors if you're on the roof, or if you have more than 3 current carrying conductors, or if you're in an ambient temperature greater than 104, or less than like 60 C or something. I don't know. There's all sorts of additional numbers that you have to contend with, but I at least wanted to get this out there so that you could kind of start getting your head wrapped around it, including the mark out here. So, and yes, the 2023 code still has requirements for a roof, because if you throw conductors right down on top of a roof, well, those are going to get stupid hot because a roof is hot, right? So you can't push as many amps down that thing. So we have talked about the types of voltages, nomenclature, breaker configurations, types of conductors, the size nomenclature, which is the AWG stuff, and pass these at different temperatures. That's everything I had listed today.